Okay. All right. There we go. Okay. Now it's recording. All right. And we're off. Okay. So, all right. Where are we at? What are we doing? What are we talking about? So, we are still hanging out with the Gram-Schmidt process and all the ins, the outs, and the what have yous of that. We've just begun scratching the surface. But let's kind of remind ourselves of what's going on and what we're working with. So, we've kind of returned to linear geometry. Where the key ingredient for all of that was the dot product, which is just take two elements of Rn, multiply their entries, and add them up. So more recently, we've seen how this is used in the definition of matrix multiplication and the various fun things of that. But remember that we initially introduced this and worked with it to talk about lengths and direction in Rn. So, calling things vector spaces, we want to be careful about that because the word vector has like a physics definition. A vector is something with magnitude and direction, magnitude meaning length, and direction meaning angles. And dot product is able to explain what both of those are. All right. So, while we talked about how you can use dot product to define angle between any two vectors, the main thing that we usually care about is when things are perpendicular to each other or when they're forming a right angle. The fancier word for that is orthogonal or orthogonal, if you want to be cool. Yep, and that happens when the dot product is 0. All right, so one of the main things about perpendicularity and dot products that we have available to us is that given any two vectors, we can project one onto another, and here is the nice formula for it. The picture for how this all works, so here is x, here is y, and basically this component right here is this thing right here. So note, that thing is just the scalar multiple of y, so, friggin' annotate. If Charlotte was here, she would say, don't say frickin'. You'd be like, you're right, Charlie. We don't say that word. Although, we got the first F-bomb. We got the first, she said, fuck you, it was great. She had no idea what she was saying. There was, no context for it either. She just said it, and we're like, alright, great. So... Then I had to explain to her that you want to be careful with that word. All right, so this right here is a scalar multiple of y, so it's in the same direction. Those are that is a good way. Yeah, I'm allowed to say that. Oh, where she probably heard the F word. I know where it is now. I smashed my toe into the platform, our bed, or the platform our mattress is on, so, yeah. And anyway, so my pinky toe, it's all messed up. And I bumped into something, and I think I said fuck you, something I kicked by accident. So I think it might have been me. All right, but anyway, all right, so yeah, so what we can use the dot product for geometrically in Rn, so if you got a vector x and a vector y, you can project x onto y. So this thing right here is usually referred to as the projection of x onto y, right? It's onto y because it's in the same direction as y, but it's just been scaled, right? There's your scalar right there. But useful now, so that is useful, and a little later on we are going to talk about projecting onto a subspace, of which this is a special case of. And we've kind of secretly already talked about it because you use it in the Gram-Schmidt process. Yeah, I wonder if you add up a bunch of dot product speeds made. Anyway, so yeah. But then the larger thing that gets made by taking the difference of these two then gives you this vector, which is nice and perpendicular to y. So very nice. We can use dot products given two vectors to generate perpendicular things. And this projection here is going to be what we're going to be looking to generalize a little bit later today. Cool. Good stuff. Then again, here is the delightful picture for these things. All right. Nice. Okay. So we can talk about two vectors being orthogonal to each other, but we can also talk about any list being orthogonal. Just the key ingredient is distinct elements in the list must dot product to 0. So whenever you take two things with different indices, the dot product must equal 0. And as we demonstrated, such sets must be distinct and must be linearly independent, so long as you don't have any zeros flying around. If zeros are in there, then 0 is perpendicular to everything because the dot product. So the 0 vector is perpendicular to everything because the dot product will always equal 0. It's not interesting, so we don't include it in the discussion. All right, nice. So as then we demonstrated, it is possible to take, so every orthogonal list gives you a distinct and linearly independent set. So naturally, you want to do the reverse, given a distinct and linearly independent set. Is it orthogonal? The answer is no. You can form bases for vector spaces that fail to be perpendicular, mutually perpendicular. But you can always turn those sets into something that's perpendicular. That is the content of the Gram-Schmidt process. All right. And as we noted, the proof is there exists things that are nice. And this is a good there exists proof because it actually gives you an algorithm. It tells you how to find it. So particularly the first element in the list is the original element, and all the other ones are found recursively using this beautiful formula right here. So hey, projections, adding them all up. Isn't that a cool thing? Mm-hmm. Indeed. Cool. All right. So yeah, that kind of pretty much catches up the speed. So we talked about how to perform the Gram-Schmidt process, and then we talked about you can actually power it up a little bit if you wanted to. So instead of turning the distinct and linearly independent set into an orthogonal set, you can turn it into an orthonormal set, which is an orthogonal set with the extra condition that all of the elements are of length 1. They're unit vectors. So the only difference between orthogonal, which is uj dotted with uk is 0. So orthonormal is orthogonal with an extra condition. The normal part is just asking for the dot product of each element with itself to equal 1. So the standard basis for Rn is an orthonormal set. There are others, and the Gram-Schmidt process can be modified to give you an orthonormal set. So you either divide everything out by its length at the end, that will keep things nice and perpendicular and get all the lengths to equal 1, or you divide by the length at each step, whatever the hell you want to do. And as we are going to see, starting from this point forward and later today, orthonormal sets are the better ones because, kind of the goal is to turn a basis into an orthonormal one. Well, what do we like about bases? A basis for a vector space lets you represent any element as a linear combination. And orthonormal sets, the scalars are simply the corresponding dot products. So, you can belong to the span of a set. You know there must exist scalars, but for any general set, you don't necessarily know what the scalars might be. You just know you can find them. Orthonormal, you've got an outright formula for how to compute them. So they're better. They're much better. All right, and as we go forward today, we'll see that not only are they much better, they are, you want to work with orthonormal things. Even if it does, as we've already discussed. So here we did an example of using the Gram-Schmidt process orthonormally, where you have to divide it by the lengths. It's going to invariably introduce square roots, just nature of what the length of the vector is. So computationally, that can become problematic, but it's not the worst thing ever. So, all right. Okay, and so now we're back up to speed, kind of where we finished off. So, so of course we always want to connect. Anytime you're working with an idea in Rn, and it's got anything to do with the vector space structure, so or anything related with dot products, which is part of the vector space structure, you want to figure out how to tie it back to matrices one way or the other. Because, matrices are very nice. We know how to work with them, and tying a concept to matrices means that you're tying it to linear operators or linear mappings, and that's great. Linear things are the best. I can't tell you how much of math is devoted to how do I turn this into something that's linear. It is no joke saying that, a lot of mathematics boils down to, okay, how do I turn this into a matrix? Or how do I get a matrix in here to help me out? Even when you're doing crazy, ridiculous functional analysis stuff. So for example, a problem I was working on Um, I was infinite dimensional linear operator nonsense stuff, but you could turn it into a 2 by 2 matrix problem if you looked at it the right way, basically. So it's even when you're working with really abstract nonsense, a lot of your work will eventually turn into, all right, what's the matrix? What matrix is going to help me? So tying any new idea you cook up in Rn into a matrix is always a good move. So orthonormal is a concept of, right, the dot products are behaving in a very certain way. Matrix multiplication is built off of dot product, so pretty natural to then go over to here. And indeed, so a invertible n by n matrix is said to be orthogonal if its inverse is its transpose. That's just a natural thing to consider. And as we're about to prove, this happens precisely when the columns of the matrix are orthonormal. So if you have a set in Rn, and you want to know if it's orthonormal, all right, well, smash its columns together, create your n by n matrix, and then prove that that matrix is invertible and its inverse is its transpose. Or the reverse, use the Gram-Schmidt process to create an orthonormal set. Hey, you've got a matrix that is invertible and its inverse is its transpose. So you can go both ways there. It's an if and only if. Good news. All right, nice. So yeah, so here again, kind of the idea is we're tying this idea of the vector space structure to a matrix idea. So a move that you'll do quite a bit. All right, so let's do this proof. All right, and it turns out that there's really not too much going on in this proof because the secret sauce to this is something we've already discussed, which is matrix multiplication is dot products in disguise. So if you're orthogonal, that means your transpose is your inverse. So that means A transpose A is A inverse times A, which is the identity. And equipped with that now, we now know this product is equal to the identity, all right? Well, if you look at the jkth entry of the product, that is the dot product of the jth row of the left with the kth column of the right. Oh, and when you know it, you got a transpose right there. So this just turns into the jth column. So, hey, the dot products of the jth column with the kth column is always equal to the jkth entry of the identity matrix. So when they're distinct, it's 0, and when they're the same, it's 1. So you've got an orthonormal set. Yay! Proof's over. At least the first part. Well, the entire proof is over, because, of course, this is an if and only if where after you've proven the forward direction, the reverse direction is read this backwards appropriately. So mutatis mutandis, favorite Latin phrase that I'm sure I'm not pronouncing correctly. Yeah, so there we go. Right, note, right, this is not super unexpected, right? If we're really thinking of, like, okay, write out what it means for your inverse to be your transpose. A transpose A must equal the identity, and then, oh, hey, what's the jkth entry of the product here? It's the dot product of the jth row with the kth column, and, right, and from there, like, it's oh, and then this, and then this, and then this. So it's a good and then proof. So right, a great just unraveling definitions. It's good stuff. Okay. All right. Now, so before we do the reverse direction of this proof and just read it backwards, basically, just cleverly, I want to stress something right now. This is our first taste of A transpose A. Like I said, when we first learned about transpose, it's like, this is, sure, kind of at first, it's like, this is something you can do. Yay. That right there. I cannot even begin to tell you how much mathematics starts with that. Like I was saying earlier today, towards the end of the class, I'm going to talk about SVD, which is going to go a little bit outside of our textbook. Guess what the first step is? And in fact, so my advisor works for the Department of Energy, and so he basically he's like a manager now, essentially. He just directs team to do research. And something, last time I was talking to him, something he was stressing was like, A transpose A. Every single thing we do in whatever like experiments they're running. It's like everything we do, you start with A transpose A. We collect data, A transpose A. First thing you do. So here is our first taste of what is probably not like the most important, but definitely a. Let me rephrase it. Like depending on what math pathway you go, you're going to see A transpose a lot. So here's our first taste of it. We'll get a lot more of it later on. Okay. All right. But we still have to finish the proof, so let's do the reverse direction. So suppose a set's orthonormal. What does that mean? That means that the dot product is equal to 0 when the indices are different, and the lengths are all equal to 1, or in other words, the dot products are equal to 1. All right, so given any jk, if you look at the jkth entry of this product, as we just verified, that is the jth column dotted with the kth column. Normally, it's the jth row dotted with the kth row, but the A transpose here doesn't give you the right. The jth row of A transpose is the jth column of A. Right, the transpose interchanges rows and columns. All right, so our hypothesis then guarantees that this that the jkth entry of this matrix multiplication is equal to 0 whenever j and k are different. So it is the jkth entry of the identity matrix. And if j and k are equal to 0, right, the jkth entry is the dot product of the vector itself, which is equal to its length squared. Its length is 1, so squaring it gives you 1. Since j and k are equal, that is the jkth entry of the identity matrix. So A transpose A is equal to the identity. And there you go. That is enough to tell me that A is invertible, and its inverse is A transpose. Because again, when verifying that something is invertible, you just need to show that one product works. As we verified, so that makes matrix multiplication very nice. All right, beautiful. So there we go. So we've been able to connect the idea of orthonormal to matrices. So, right, a set's orthonormal precisely if the matrix, when glued together, gives you a nice invertible one whose inverse is its transpose. So now that we've brought matrices into the fold here, matrices, again, are the quintessential example of linear operators. So let's see where that takes us. So before we get there, one little pit stop to help you with problem number 2 on your homework. So problem number 2 asks you to prove that, so let me pull up problem number 7 quickly here. Come on. All right. There it is. So problem number 7 asks you to prove that if you have an orthogonal matrix, A times X and X will always have the same length regardless of the X you choose. And I wonder if that's just this written in a different way. Not fully. There's still there's a little trap you can fall into, so be a little mindful. But anyway, yes. All right. So indeed, this is true. So let's remind ourselves of some things. A times X. So if you look at A times X, transpose, so remember the way matrix multiplication works, transposing a product is the product, but you reverse the transposes. So that happens right here. Now we've got A transpose A, that's the same thing as A inverse A. That product is the identity, and that gives us X transpose Y, and now if you think about what that actually is, you'll see that that is indeed the dot product. So think about how this swaps, and right. So you take X and you do that, and then you do matrix multiplication, which is the dot product. So it is literally what the dot product is equal to. Cool. Yeah. So another way of thinking about the dot product is that it is X transpose Y, which, as we just saw here, does pop up every so often. So it's pretty neat. So yeah, that's a slick move. But, and in some like books, they'll define dot product as X transpose Y. So there's some things you can do there. But anyway, beautiful. All right, cool. So I can use this for problem number 2. And like I said, it's there's kind of a clean way of doing it, but be a little careful. There's a trap you can fall into. All right. Okay. Now, with all of that said, now that we've been able to attach this idea of orthonormal elements of Rn to matrices, matrices are all about linear mappings. So once matrices come to the discussion, naturally we want to see, all right, well, I bet there's some things we can do with linear mappings and orthonormal sets. And the answer is, oh boy, can we. All right. So let's motivate where we're going to go with next and motivate what problem number 3 is asking you to do. Find the mid-substitution of the projection. So let's explain what projection is going to mean exactly. All right, so consider the following subspaces of R3. Okay, so what do we have here? So we have the span of 2 elements, and we got the span of 1 element. Now, I don't know what I couldn't give you the exact picture, but an idea of what these look like. So this is the span of 2 elements, so that means this thing is something like a plane, right? So it's 2 points, and you're looking at the span, so it's the plane that contains those 2 points. And this thing would look like what? Well, it's the span of a single vector, so it's just going to look like a line, right? It's going to be all scalar multiples of the element 1, 0, negative 1. Okay. So if I were to, I don't know, take these and like do that, and then that's not the best line. Yeah. And yeah, maybe more like that. It's a line like that. And if I bring this over here and then do like a little dotted line right there and draw a whole little right angle right there, ooh, that'd be great, right? Yeah, that'd be pretty cool if M and N were perpendicular to each other in that way. Now, if that were to be true, what would we need to know? Well, we would need to know that, right, this line right here, so that vector, would form a right angle with anything that lived here. So anything that was a scalar, an element of this set, right? If we were going to have this beautiful right angle thing happen, that could only happen if these two things dotted with that was equal to 0. So let's point out that this subspace has the following wonderful properties. Okay. So the first thing is that their intersection is just a single point. So if we think back to that picture I was drawing, so again, the picture to keep in mind while we're talking about this is, let me do like that, and then dot, 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 and then like that. So it's a little bit more. Yeah, so indeed, M is a subspace and N is a subspace, so their intersection is always going to have the 0 vector, right? Every subspace must have the additive identity in it. So, but, right, if we look at this picture, we see that, yeah, the only place they could intersect would be that, right? This picture is to be believed. All right, so let's actually verify that. So let's let X be an M and X be an N. If X is an M, then it's that, and if X is an N, it's equal to that. Okay, so in other words, so if we were to do X minus X, then you would have this plus this minus this, which is equal to that. And, oh, hey, you got a linear combination equal to 0, and if you look at these, you'll go, oh, wait, hey, those are linearly independent. So you need to check that, but it's not too hard to see that they are because they're orthogonal, by the way. So that would force A, B, and C equal 0. There we go. So, right, a little bit of work that I'm not including here, but you could verify that these vectors are linearly independent, so all those scalars must equal 0. All right, so, hey, there we go. The intersection of these two is trivial. And next up, given any element of R3, R3 can be written as a summation of something from M and something from N. And like I've already let slip, this must be a linearly independent set. right? Even though this is the negative of it, you could pull the negative out and suck it into the C right there. So this must be a basis. So this just naturally pops out. Okay. And the dot product of x with anything out of m with anything out of y, the dot product there is equal to 0. Right, and then that's just a quick little calculation. Do this dotted with that, you'll get this. And this dot products to 0, because 1 dot over 1 is 1, 0 dot over 0 is 0, 1 dot over negative 1 is 0. And here, right, zeros are in precisely the right spot to 0 out, so the AC and the BC literally do not matter. Okay. Right, because again, anything that's in M is a linear combination of those two vectors, and anything in N is just the scalar multiple of this one. All right, so these two subspaces of R3 have the following three properties. Their intersection is trivial. The only thing in their intersection is the 0 vector. Everything in R3 can be written as a summation of the two things, so that's kind of neat. And the dot products of any element out of M and any element out of N must equal 0. So it has these three key properties. All right. So again, the image to be keeping in your mind while we're talking about these ideas. So we've got a subspace M. It's generated by two things, so it looks like a plane. N here is a span of a single element, so it looks like a line. And these just so happen to work out that the intersection of them is trivial, and that intersection that they have forms a nice right angle. So in other words, another way of saying this line is perpendicular to that plane. So another way if I think about it from like a Calc 3 perspective, I've got the normal to the plane. We're not going to get sweaty about that stuff, so if you have like traumatic memories of Calc 3 and normal vectors and things like that, and cross products and all that other stuff, don't worry, we're not going to do that. But just connecting it to things you may have heard of before. And also, spoilers, you really need to take linear algebra. If you have linear algebra before Calc 3, that makes Calc 3 a hell of a lot easier. There's a lot of stuff in Calc 3 where you're just like, you're like sidestepping the fact that it's like, this is a matrix. These are linear transforms. Don't tell anybody. So, like coordinate transformation. Like, it's like, yeah, it's because there's a matrix. Yeah. All right, cool. So this idea here of like a subspace being perpendicular to another one, that's our goal to go after now. The idea of that are what are called orthogonal complements, if you're looking ahead in the book. So that's our goal now. So we have this nice little example to always keep in mind and go back to, but we want to now look at subspaces, pairs of subspaces that possess these three key properties. So their intersection is trivial. Their every element is represented as a sum of two of them, and the subspaces are perpendicular to each other in terms of dot producting in that very particular way. All right. So it turns out that you can always do this. In fact, you don't even need two subspaces. You just need one subspace, and then you can, given a subspace, you can always create n. So when I actually did this example, I didn't just pull these out of thin air. I just took this one up first, and then I computed what this needed to be. There's a way of getting that, as we will see. So this is our next goal, is to play around with this stuff, and this is going to tie into this idea of projecting onto a subspace in Rn. So as we're going to see, it's a cool idea. All right, so that's our next big goal, is to look at subspaces where I can pull off these three key properties. So, all right, and here's a reference to an episode of Tim and Eric, and if anybody knows, immediately, high fives all around. And if you have no idea what I'm talking about, then congratulations. It's better that you don't know. All right. So, given a subspace of Rn, we define its orthogonal complement to be the collection of things that are perpendicular to it. Okay, so in the previous example that we just talked about, indeed, the orthogonal complement of the span of these two things is the span of that. So given a subspace, we can create its orthogonal complement by looking at all of the things that are perpendicular to every element in there. And so the example you always want to keep in mind is the one we were just talking about, which is it's a plane and then a line going through the plane that's perpendicular to it. So if you like your Calc 3 stuff, right, I'm talking about the normal to a plane. So this is just a fancier, more abstract way of capturing that idea. All right, so let's actually verify that this is indeed true. So given any, and this will serve as an example to get us used to working with this, because when I first saw this stuff, this definition always like caught me off guard. This one I always had to like really think about, like, okay, the collection of all things that are perpendicular to everything out of M. So it was always I always had a hard time working with it, and when it came to proofs, like the idea, like I always in my head was like, okay, a line through a plane, gotcha. But working with them, I always thought it was a little tricky. So let's explicitly verify that the two subspaces we were just talking about, the orthogonal complement of M is indeed M. All right, so let X be in here. That in order to be in the set, that means that this dotted with anything from the set, so ignoring that part, needs to equal 0. So you're in this set precisely if the dot product of X with anything from the set is a linear combination of those two elements, that dot product is 0. So you're in the perpendicular of this set, the orthogonal complement, if your dot product with any element in here, which would be a linear combo, is equal to 0. So it's the collection of all things that are perpendicular to the elements in here. So any element that lives in the span here, right, they have to look like A, B, A, just do the linear combo. So that means we've got 0 is equal to that right there. And that's got to be true for all real numbers A and B. Right, so what do I want to prove? I want to prove that X must belong to this set. So that means that X needs to be a scalar multiple of 1, 0, negative 1. So I know this has to always equal 0 for all choices of A and B, so let me be clever about how I choose A and B. So first of all, if I choose A equals 0 and B equals 1, these 0 out and B is equal to 1, so that forces X2 to always equal 0. And then choosing A equals 1 and B equals 0, that zeroes this out, and then I get X plus X1 plus X3 is 0, so X3 must be negative X1. So in other words, X is in this set if and only if X3 is equal to negative X1 and X2 is 0. So in other words, X has to be a scalar multiple of 1, 0, negative 1. So in other words, I'm in the span of this set. So like I said, when I put this example together, I didn't just start with M and N. I started with M, and then I figured out what its orthogonal complement had to be by doing this work to get that X has to be a scalar multiple of 1, 0, negative 1. Okay. Okay, so oh yeah, let me explain the dumb joke. So this set is usually referred to as M perp for perpendicular. So that's how you communicate this out loud to other mathematicians. Right, the formal name for this is the orthogonal complement of M, but that's a bit of a mouthful. So if you just say M perp, people will know what you're talking about. So, right, so the secret code language that we have to signal to others that we're mathematicians. Which is, side story, so one of my all-time favorite mathematicians is a guy named Stefan Banach. So if you don't know him, he's a good mathematician to know. He is probably, I would argue, the most important mathematician of the 20th century. I'm sure somebody would say that's a big oversell, but the work he did was so much math is built off of his ideas. But anyway, so the only reason he even became a mathematician, he didn't have a PhD or anything for the longest time. He was just kind of casually interested in mathematics. So him and his friend, who was also in the math for funsies, oh, what's his first name? I don't remember his first name. His last name's Nicodem. Um, they're hanging out in a park and they're talking about Lebesgue integration, which at the time was like cutting edge stuff. And so they're just casually talking about Lebesgue integration out loud at a park. And Hugo, not Stein, it's Steinhaus, that's what it is. So Steinhaus, who was a professor at the local university, just so happens to be walking in this park and he overhears people talking about Lebesgue integration. And so he's like, wait, what? And so he came over, he's like, what? How the hell do you guys know what that is? So, and then from there, they got talking, and then Steinhaus was like, hey, Stefan Banach, I got this problem. Can you figure this out? And took Banach the rest of the day, but he solves it, and it's the Banach-Steinhaus theorem. It's like one of those like fundamental results in functional analysis that he just casually solves. It's ridiculous. And then from there, he basically tricked Banach into getting a PhD. It was a fun story there, so check that out. Because Banach didn't want to go for the hassle of getting it. So yeah, neat stuff with that. So yeah, the sort of like the dumb code language we use. You never know when you're out in public talking about M-perp. Catch somebody's ears, and they'll come by and be like, "Hey, you want to do some inner products?" That's the move. So yeah, just loudly talk about orthogonal complements. You'll make friends. All right. Okay, so all right, let's set up now some nice things. So as we already have seen, so note, remember what I said when we were talking about these two subspaces? They have these three really nice properties. I wonder, and as we just verified, we now know that N is the orthogonal complement of M. I wonder if the orthogonal complement always comes with some nice properties, like, I don't know, almost all of these. All right, so let's verify that indeed. If you have yourself a subspace, then its perpendicular, its M-perp, its orthogonal complement, is indeed also a subspace. So that comes for free. The intersection is trivial. Good news. So that first property was for free. Note that third property now is also for free, because this is literally just the definition of being an orthogonal complement. Yeah. And as we will now verify, as it turns out, if you've got obviously you can take the orthogonal complement of a subspace. Naturally, if you're talking about a process that you can apply to a subspace, you want to go, what happens when I apply this to the trivial ones? What happens when I apply it to the subspace that has the least number of stuff in it? So the subspace just consisting of the zero element. Turns out the perpendicular of that is all of Rn. And then likewise, if you were to take the perp of Rn, what do you get? You get the trivial one. So there is a nice little relationship between those two. Okay, so now I got 2 minutes. Let's just stop for right now. So next time we will prove that M perp has these nice properties, and then after we do that, here's not going too far away. We'll then prove some other neat stuff. So one of my favorite results is this one, that the perp of the column space is the null space of A transpose. That's a fun little result. Like it turns into a T. You pull it in and it turns into a T. This is the only reason they came up with T for transpose. That's why they called it a transpose. True story. And then we will prove the summation property, and that will be the exciting one. Okay, so that's where we're going next. So next time we'll jump into these results, prove them, and move towards defining what the actual projection is and talking about how to get its matrix. So that will be the goal for tomorrow. All right. Cool. All right. So again, that's it for today. So I'll stop the recording.